be here and again in this workshop. So I must admit that I have prepared this presentation to be very easy in light of time, but also of my poor sleep the past night. So hopefully we can go through this in a very relaxed way. And in fact, because we are not at a conference but more a cozy setting, I would like to start with a question for you. Why do we need time and space resolved energy system models? And if it works, let's see. No, it doesn't. Huh? It doesn't at all. Okay. Well, we skip that then because it was a VOOC lab where you had to vote to actually put in stuff, but I have no clue why transitioning to a different computer it doesn't work. Or, yeah, no matter. Okay. I give you my answers. That, of course, are only partial. So that's a bit how we like to use system optimization in our group. So to support better understanding of non-intuitive complex systems. When I was a PhD, I really didn't want to go into optimization. I was always of the belief, I understand this. I can understand how it works. Let me look at the physics. Then I realized when you go with the time, and you have millions of variables, right? Forget about it. Second, as Luca already mentioned, to guide technology development, identifying the required features based on the expected operation. And last, very broadly, to support decision-making of relevant stakeholders. Now, last year, I talked about this because I have just a recap on that. I showed this slide with two different technologies, and I said, well, they both failed to deliver at mass scale because of a number of common reasons. Wrong primary market, limited infrastructure, viable alternatives, lack of market, and the social acceptability. And then I concluded technologies need to be developed while evaluating their role in the broad energy material transition. And I think Luca gave a nice example of what we can do. Right? Today I will talk about the last point, to support decision-making of relevant stakeholders. And I would like to do that by looking at the strange case of Dr. Jekyll and Mr. Hyde. So who is Dr. Jekyll? Is the Irsching 4 power plant. So a German power plant. I have nothing against German power plants. I think that I could have taken Tavazzano, which is a natural gas combined cycle in Lombardy. The story will be the same. And who is Mr. Hyde? Is the Irsching 4 power plant. And why is that the reason? So before I want to just say a few words about the plant. So it's a very modern combined plant. It's a Siemens H-class gas turbine with a cycle efficiency of 60.4%, 561 megawatt. But how would I describe it? I'm Italian, so right, I took a Ferrari and a typical Italian town. It's a Ferrari in a very small and old street. It will never or hardly run at 60.4%. And there is a little bit of a history behind it. So let's look at this history. So 2011, commercial operation begins. Fantastic. Soon after, certified for setting a world record in efficiency over 60% in the news. That's why how I know it, because it was in the news. Power Mag, I think. Then, few years later, March 2015, closure notification. Here we get Mr. Hyde. Due to the rise of renewable energy and favorable market condition, high gas and lower prices. 2016, mothballed, almost dead, and put in grid reserve, saved by grid reserve. The plant was officially mothballed and for commercial operation, but was simultaneously contracted by TenNet to be part of the grid reserve. Nicely, 2020, reopened for commercial operation. The plant was officially returned to commercial electricity market. So this, what does it tell? What does it tell? This story is that when you have a power plant, essentially you can easily turn it on, turn it off, also put it on the market, retire it, a company can handle losing this asset in a way. But it is not always the case. So if you have a complex infrastructure, you can't just switch off the power grid, right? Like electrical engineers know very well, when they study the electric grid, they start from the existing grid. But the same applies to renewables. So you're not going to build a huge wind farm or a very nice solar park in the middle of the desert to switch it off the day after or 5 years after. You need to keep them, and you need to consider them in the energy system optimization that you want to do. Even more critical are chemical plants. So here you see the port of Rotterdam. Here it's basically it's much larger than Rotterdam itself. So all this is a large chemical cluster and a harbor. And here you see the Ludwigshafen, BASF, a bit more dense, but also not something you can turn on and off in a few years. And I think that in Austria you also have some steel mill plant that may be very well associated to a chemical plant. Chemical clusters are in fact in a perfect storm in terms of large legacy infrastructure. So this is a bit to come to my point that in many cases we need to consider the role of existing infrastructure and move away from a greenfield approach to brownfield approach. Now, this comes with a lot of computational challenge. And here I'm referring not only to the fact that you have an existing infrastructure, but that you need to look at multiple years. So I have a transition study, look at the development over a number of years. Now, I'm just summarizing a few things that you know perfectly, probably. So the time horizon needs to at least cover the lifetime, 25, 30 years in industrial settings. Maybe nuclear plants are a bit different. Also, if you work with buildings will typically have a higher lifetime, longer lifetime. But however, usually 25, 30 years, and the decisions at the year T depend on the remaining useful life of the asset and the performance at the year time minus one. So the optimal solution needs to understand when to invest. The key word is when to invest. Right, time discretization, right? We have hourly discretization. We need to still understand retain the physical fluctuation of the system, electricity price vary. We need to have a look at the hourly resolution, but not only that, also renewables, the variation in wind and irradiation. Another complexity is the set of technologies. We need to have a fair portfolio of different alternatives compared to the existing one. And this answers the question to what to invest. Optimal solutions are needed for what to invest. Not last, everything is basically embedded within a varying boundary condition. So you have a lot of things that change over the year. We saw in some posters and in some talk the weather, the CO2 price, the demand. They have a large effect over a long time horizon. And of course, these add to the natural stochasticity of many variables. So we easily end up in Sonia's 600 million variables. You have tens of millions of continuous variables, hundreds of thousands, millions of binary variables. Now, let's take a little step back and see how we can include existing infrastructure. So I don't want to be very comprehensive. This is just a few methods that we can use. So one is there is a typo here, sorry, okay. Input data, I think I modified only one slide. Input data, so along with, I would say, a myopic time period division. So if you represent well the system and you look at different periods with a myopic capability of predicting what is changing, so you can have a snapshot of the current situation and bring forward this snapshot in different periods. This is very easy to implement, has almost no time in the implementation. but it requires a lot of data. Getting the data, probably you all know how difficult that is, and getting good quality data. And it works well for representing the system at the current state. I think, though, that it's very time-consuming, and it's not nice to look for data, but this is something that we must do in any case, even in the greenfield cases. Now, then we can go to, let's say, the holy grail, multi-year, single stage with perfect foresight. So in one formulation, you solve all the system. It's very elegant. It leads to what could be the true optimal and avoids lock-in, but it's computationally the most challenging. And also, one may question, well, perfect foresight is not really a good representation of the real world. And it's important to note that if you're using an existing framework, it's not necessarily true that or easy to adapt that framework to a multi-year single stage with perfect foresight. As a last possibility is a multi-year with rolling horizon. Now you have a sequence of resolution for different time periods. Here, in this case, complexity can be managed, and implementation, let's say, is simple enough, and is also aligned with how the real world behaves. So you have moments where you decide what to do, what to invest. And yes, if you invested in Dr. Jekyll, you need to deal with that, right? It's in your portfolio. Of course, here we have a risk of suboptimal, long-term lock-in. We have fixed parameters for the years in the time window. And it probably is the most used approach for multi-year MLP problems. All right. To add to this, in all cases, deterministic model can and should be extended into stochastic dynamic programming. All right. So, well, again, here it's really a few words that I don't want to be very specific. So there are plentiful of methods. We basically heard about possible nice and useful methods so far. I would say two big families: data aggregation, time, space, clustering, and then breaking up the problem in multiple problems. Partial, Bender's decomposition or Bender's decomposition, surrogate models with or without machine learning, you name it. And these are all helpful. All right, now, this was kind of a teaser. I would now like to discuss a couple of cases that we examined, but I will first start with quickly introducing the modeling framework that we use. It's not your ERC, but it sounds similar, Adopt Net Zero. And I also wanted to stress that the work that I'm presenting, example 1 and 2, is part of the PhD thesis of Julia that we have here, and Jan that we had last year, and unfortunately couldn't be here this year. Now, Adopt Net Zero is an open software. We publish it in the Journal of Open Source Software, and essentially is a tool that has a bit of a technical, as you might have seen already from Luca's presentation, a technical hat, where we can do optimization of multi-energy system with mixed integral linear programming or linear programming, and it can model a variety of different systems, from individual technologies to industrial cluster, regions, multiple countries. Here you see some parameters. Maybe I don't need to go into the detail of those parameters. So it connects an input to the demand. The demand can, again, be very generic. Here, this example is electricity, hydrogen, and heat. We have a large number of technologies. That this is not representative of all technologies, are just a few examples. And it connects to the required input. This is for one node, and we have it can model a network with a certain limited capacity, though. So I think that other models like PIPESA do large networks much better than Adopt Net Zero. But still, you can model a network of maybe 20, 30 nodes. Yeah, so it's formulated as as in the most generic way, the mixed integral linear programming framework, and we have input data that include weather, space description, user demands, energy prices, carbon rates, technology and cost performance. Decision variables include the technology selection, the sizing, using different approaches for example, to account for performance at different size, scheduling, of course, the operating load, the network size and operation, and what comes in and out from every node. Constraints include technology behavior, the capacity of network and behavior, and the energy balances, of course, per node and the total. And finally, we can optimize for costs, but also for emissions. And we see that changing objective function, it helps a lot sometimes. So, for example, in some cases, the case that I will show later, we also optimize for the maximum energy production. If you have a wind farm, for example, Matteo is now optimizing for the total length, we are trying at least, the total length of hydrogen pipelines under a certain cost constraint. So we have flexibility with the objective function. Just to say that costs and emission are not necessarily everything we need to optimize. And yeah, so I would like to start by discussing the North Sea energy system. And this was part of Jan's project. And essentially, we have a possible future powerhouse of Europe, the North Sea. This is shared by several countries. And we wanted to understand how this system should evolve, should look and evolve in time, considering the wind potential. And also the use of existing infrastructure that is present in the North Sea. So the North Sea is definitely not an empty infrastructure. There is plenty of stuff, most notably natural gas pipelines, but also more and more electricity cables. And that you have areas that need to be maintained for fishing, for some military activities. So there are plenty of stuff, and we need to understand how this basically region need to be optimally parceled and used for the energy system. What did we do? So we started by looking at the existing infrastructure. This basically means data collection. Today, there is an existing electricity grid, there is an existing many offshore pipelines, and there are existing generation and storage assets around and within the North Sea. Then we looked at 2030 and 2040, so the evolution through these 2 decades. For the 2030, we said, well, we could optimize the system, but do we need to do that? In fact, there is already the TYNDP plans. There are already national tenders, if they are successful, because this is also something to be seen. Recently, in the Netherlands, a national tender went completely empty. And UK, it happened for a couple of times. So we took this as, let's say, what will be the energy system in 2030, but we did allow for some flexibility in it. So, first of all, the operation of all dispatchable assets, and we allow for electricity grid expansion, and also for the use of hydrogen. So, producing hydrogen with electrolyzer, using hydrogen with fuel cells, and of course, transporting onshore and offshore. New batteries were also possible, and the expansion of the grid, of the hydrogen grid was also possible, notably onshore, but also offshore. So we considered the production of hydrogen also offshore. This is something that some Dutch association like a lot. Yeah. Then we went to, we follow with the 2040, and in 2040 there is more freedom to play. So we allow for the expansion of the renewable generation. And again, with all basically the possible possible options of 2030. So the infrastructure development. Now, the baseline is what we have today, and this is represented overall by this system. In the offshore node, we have wind farms and transmission, and onshore, we have a number of different renewable and non-renewable assets, but also we have a hydrogen demand. So there is an existing hydrogen demand today that is supplied with natural gas reforming. This is the 2030 baseline. So you see here, essentially, this is a sort of validation of the TYNDP. We were quite happy to see that we could find a solution for the design of TYNDP. And you see specifically for every country, every node, the different set of generation portfolio and also how the demand of hydrogen is satisfied and the electricity demand is satisfied. All right, but what about the expansion of the infrastructure? I would like to focus now on two. First, the electricity grid, and then the hydrogen. So what you see here is the electricity grid expansion with the costs, the emissions, and the cost per ton of CO2. And you have a reference case, the TYNDP, and then we allow for multiple expansions. So we have the case synergies, look at it all, so where we allow onshore, offshore, and cross-border expansion of the electricity grid. We have the case where we don't allow for international expansion. We only allow for onshore grid expansion and only offshore grid expansion. And what you see is essentially that by improving the electricity grid, especially when allowing for offshore and cross-border expansion, we do get a reduction of costs, and that comes with a reduction in emission as well, simply because we are using the electricity generated by the wind farms. Then what about hydrogen? We have a similar case. We depart from the TYNDP reference case, and then we have a number of scenarios. So the expansion of hydrogen only offshore, where we don't have any storage, where we don't have transport, and where we only look at onshore. And essentially what you see is that the expanding the hydrogen infrastructure helps, but a tiny bit, not much. So if you need to improve the infrastructure of the North Sea, you better put your money, or our taxpayer money, into the electricity grid. Then we went to the 2040. And the 2040, again, you have now here the transmission expansion, the hydrogen, and also the electricity storage, which in the interest of time, I didn't discuss for 2030. And essentially, again, you see that that the electricity infrastructure is really the key to improve the energy system of the North Sea, and that this comes with also quite substantial additional capacities of renewable in terms of offshore and onshore wind. All right, let's move now to the second case, the chemical industry. Now, the chemical industry is quite a case because there is a large fleet of existing plants, and operators need to decide what to do with those plants. In the Netherlands, for example, we are seeing that a substantial number of companies are leaving because there are no more the conditions to operate with a nice economic return. Around 30% of the existing assets will need to have a decision on what to do with the investment or to extend their operational lifetime. So this is also an opportunity for new technologies to understand and to see if we can go away from the existing technology portfolio and invest in new technologies that have a lower emissions. And finally, there is no greenfield case for the chemical industry in Europe. I guess that wherever country you pick, ask to have a new chemical plant. Ask the population. No way to build a new chemical plant. So it's very important, it's fundamental that when looking at the transition of the chemical industry, we do that departing from the existing plants. Yeah, it's complicated, but it's what we have in Europe. And a valid approach could be that we don't do any chemical synthesis in Europe anymore. Then we may go to a question of security of supply, but that's a bit of another story. So again, it is important to develop the tools that can support the long-term decision. And what complicates this is also that the investments are very large as well. So much more than a natural gas combined cycle. They are always in a number of billions. I would like to discuss the case study of the Netherlands. Actually, it's not the port of Rotterdam, but I will show that later. And what did we do? What Julia came up with? Here you see the short-term, mid-term, and long-term time horizon. And in the traditional greenfield approach, what we would do is, well, we run the optimization for the short term, so 2030, say. And we get a number of optimal solution. We bring this optimal solution as an input to the midterm, rerun the midterm, and so on and so forth to the long term. So this is kind of the multi-period myopic with data gathering that I was talking about before. The problem here is that you have a large infrastructure present, and this infrastructure has a certain discount period. So when building that, you're accounting that you will operate that plant for a number of years. So you need to consider that cost in your optimization. So we came up with a brownfield approach where we don't jump like this, but we follow a straight line that is, we start from the current layout, we do the short term, we get the optimal solution, we retain the capacities, and we go to the next, and so on and so forth. And when doing this, you bring forward also the remaining lifetime of the infrastructure. So when you operate for the midterm, and you have a plant that has a lifetime of 30 years, and you have 10 years already elapsed, you need to account that you will have to account for the cost of the remaining 20 years. We run two different case studies, two existing plants. So this is Zeeland is a chemical cluster in the south of the Netherlands. Well, both are south of the Netherlands, Camelot. Both clusters produce in large amounts ammonia and ethylene. They are also used. They are used for other chemicals, but we look at these platform molecules, ammonia, that is used for fertilizers, and ethylene that is essentially used for plastics. And this is about the technologies. So this is the portfolio of possible technologies. It's way larger than what we have in the electricity domain. So you really have many different ways to produce these chemicals. I will try to guide you a bit through this. Do I have the time? I still have 10 minutes, okay. So on top, you see the conventional fossil-based. So these are crackers for ethylene and, let's say, the reforming of natural gas plus the Haber-Bosch to produce ammonia. You can still use this now with a bio-based feedstock. So you can substitute, that is why /green, you can use a bio-based biogas, for example. Well, maybe. Then you can electrify the process. Electrification is in yellow. So now the cracker runs on electricity. The reformer also runs on electricity. You avoid the scope 1 emissions, but you still have all the emissions associated to the products, scope 3. Then you can completely change the technology, so you don't rely on the conventional ones, but you go to different type of processes. So this will be, for example, making ammonia with green hydrogen, with electrolysis, or making olefins, ethylene and polyethylene, with electrolysis of CO2, CO2 electrolysis. The other possibility is to stick to the thermal route, where you have what is called a reverse water gas shift. So you start from hydrogen and CO2, and you get a syngas. This syngas can be transformed into methanol, and methanol is a platform molecule that you can use for olefins. Methanol to olefins, MTO. And then there is the nice opportunities for plastic recycling, so plastic waste, plastic gasification, and biomass. Even within this, we could have tens of different solutions, but we stick to gasification, which is the one that allows for big sizes. And also we consider the ethanol and propane, bioethanol and biopropane routes that especially are important for when imported from, for example, Brazil. Now, these are all options. So you need to, that's where a complex part of the mixed integral decision come in. You need to decide which of these technologies need to be selected. All right, let's look at some result. So we start from the current layout, and you see here the case of Camelot, the big one of the two examples that I showed, and we are comparing brownfield on the bottom and the greenfield on the top. Now, the current layout in the greenfield, we don't see anything, and the brownfield is all is fossil. 2030, so the short term, you see that basically ammonia switches to hydrogen and electrification, while ethylene is basically relying on a combination of plastic gasification and biomass. The two things are the same for the greenfield and the brownfield. Now, here you start when we go to 2040, and here it's important to note that in 2030 we just minimize the cost, while in 2040 we also ask for an emission reduction, minus 50% of all emissions, scope 1, 2, and 3. And now you see some differences arising. So the ammonia case, the use of fossil natural gas with SMR plus CO2 capture is optimal, of course, because you are not considering this asset when doing the 2040, sorry, while in the brownfield, you rather stick to the electric SMR because you have already installed in the previous year. And you can now play a bit with tuning the remaining things. For example, the propanol dehydrogenation is mothballed in a way, while CO2 capture is installed to allow for synergies with the plastic gasification and the CO2 electrolysis. Continuing to the 2050, we get another switch for the greenfield. It doesn't cost to replace this SMR. You just go for the most cost-efficient technology, while the brownfield approach considers again that we need to build up on the previous solution. And you see here just tuning of the sizes, so adding elements to the existing infrastructure. So there are some minor differences in capacities. Some assets become obsolete in 2050. The difference in cost is in around 5 to 14%, and I'm showing here. What is interesting is in this graph that shows the years versus the cost, is that the greenfield, the cluster cost, is always cheaper, but the difference is not very large. So the brownfield is very close to the green field. So when you have legacy equipment, it doesn't necessarily mean that you will be very far away from the cost solution. You might be very far away in terms of technologies, but it doesn't mean that it is going to cost much more than the optimal greenfield approach. And then you can nicely show the transition in a similar graph where you see, for example, for Camelot, again, over the years, how the different technologies are adopted through the time. And I think that this is it's a nice outcome to give to decision makers, for example, in the chemical companies. All right, then I would like to conclude, even with a bit of time left. So I think that transition studies are difficult, but can really provide new insights that are needed for many problems that we have to deal with. Existing infrastructure, especially when it's complex, and more especially when we deal with the old continent, or probably this would also apply to many locations in the US, needs to be included from the beginning. And there are a plethora of methods that can allow for, and I see this community working very much on making better methods that we can use to tackle the complexity arising from these transition studies. And with this, I'm very happy to discuss these results.